All right, good afternoon. So today I want to introduce some resources from our Chih-Yuan Center. If you need it, you may use it. So, okay, everybody know we have a Chih-Yuan Center, and then they have some GPUs. I should say they have two to three GPU clusters, and you are qualified to use them. First, there are some documents. You can download them from the Google Drive. And here I briefly introduce the content of the user guides. First, now all of you have an account which can use the GPUs of the center. And your username and the password are your student ID, but the first letter is in lowercase. And everyone can use one GPU, and the model is V100 with 16 giga GPU memory, and you can use 4 threads, and the CPU model is the Intel Xeon Gold 6154, okay, and you can use 32 giga memory. And the most important is the spec can be modified by any admin users, and I am also one of the admin users. So if you need more resources, just let me know, and I can adjust your allocation. Okay. And okay, so from the left side, right hand part, you can see all of you are in the list already. But there is a problem. The problem is because some of you are enrolled in another course, say the generative AI, and I'm not sure your TA of that course has added your account into the Kubeflow system. If so, do you know your password? You know your password?
Yes.
Okay, good.
A special title class where it will show how we log in and how we create notebooks.
Okay, good. If so, then so I think half of you have the account and you have your own password already, and you can use it. And half of you who don't take the course, so your account was added by me. Okay, and so do you some of you who doesn't take the generative AI course? I think some of you only take this course rather than that course, right? If so, then your password and account will be your student ID, but the first letter will be in lowercase. Okay, so now you can use that already. Okay. And so if you want to change because that's the default password. If you want to change your password, you can go to this URL. And it uses a predefined port 31190. And if you have a laptop, you can do it right now. Try it. Okay, you will see a login user interface, and key in your username, your student ID, and your default password, and also your student ID. Then you can submit. Go to the interface, and you will see this page. It means you need to specify a new password, okay, and specify and confirm it. And you will see instruction here. It means, but however, it is not really implemented. So it means you can just ignore it and use any new password you want. Okay. Okay, then if you want to use the Kubeflow, go to this URL. So this URL is totally the same as this URL. the only difference is the port. So without the port number, go here and you will see a login dialog window like this. And key in your username and password, you can log in. Here you may see why this is my username. Why my username, the first letter is capital rather than lowercase? Because the account was created 1 year ago. And at that moment, they haven't imposed the lowercase policy. Then when you go to the Kubeflow, you will see this user interface. And let me show it right now. It looks like this. Okay. So this is the user interfaces. This is home. When you log in, you will see this user interface. And the most important part is the notebook. Okay. Here, if you use the Kubeflow first time, you will see an empty list. And here I created 3 notebooks. How to create a new notebook? Just click the add new notebook. And then you will, okay, this is the list. You can find the document from the Google Cloud. And it shows several available images for our Kubeflow system. And I personally use this one. This is the remote desktop. The ROS means robotic system. But the robotic system is not, robotic operating system. It is not important for us. The most interesting for me is it supports GPU. So here you can see. Okay. And it is a remote desktop. Okay, so there's another image called almost the same. The only difference is it is for Chinese and this is for English. Okay. So I use this because like this one. This is the image I used. Once I launch this image, I can do anything, just like I have a remote computer. So I can say launch is command line and give any command I want. I can install any programs by my own. Okay. So this is useful for you because if you want to check or examine any paper release code and you don't have a powerful, it automatically shut down because the system will detect whether there is an idle. If there is a long idle, then it will shut down your session and recycle all resources for other users. Okay. Let me go back here. All right. Okay. And then the next thing is once we want to create a new notebook, you need to give it some information. First, what's the name of this notebook or image? And then what templates do you want to use? And so here you can see I choose the desktop ROS English version 1. And how many GPU, CPU, and memory do you want to use? The CPU here means threads rather than the physical CPU. Okay. So, and currently your limits are 4, 32, and 1 here. And here usually you can specify AMD or NVIDIA GPU. For most cases, I think NVIDIA is more popular because if you want to use CUDA or CUDA, etc., it is a product of NVIDIA. Okay, then you need to specify the volume, or it means the physical SSD you want. The default size is very small. I say 10. Okay, if you let's go to see. Okay. if I create a new laptop, and here, and if I give it a name test, the default volume size is only 10 giga. It's very small. And usually, I would suggest delete the default volume and create a new volume, add a new volume here, and specify the size. Okay, say 500. Usually, I suggest 500 giga for some. If you want to install some software programs such as Stable Diffusion, you may need 20 to 50 giga, etc. And this really depends on your purpose of this image. Okay. And the volume can be shared with other image. Okay. So if possible, just use, I should say, 200, 300, 500 is fine. And then there are some options. First, there are read-write once, read-write many, and read-only or many. Just use the default read-write once. It is enough for you, because for your cases, you usually just launch a single image every time. So this read-write once is enough for you. And here, there's another option. It means the mouse path. And I suggest keep it unchanged. If you can change it to your own name, that's fine. But there will be a small problem that I will show you. Okay. And finally, because we have two different types of GPUs. One is V100. We have more than, I think, 30 or 40 V100 GPUs available. But we have less A5000 GPUs. Their performance are similar to each other. A500 may be slightly better than V100. Okay. But I suggest just keep this none. You don't need to specify which type of GPUs you want to use, so that if any GPU is available, you can just use either of them. Okay. And finally, click the launch. Then you will create a new notebook. Okay, once you created a new book, just click the run, and you will, if all the resources you want are available, then you can let your image run, and it will become an instance. So let's see here. Okay, let's see if I, for example, this one, the first one, test 24, 10, 11. Okay, this, because I need a GPU, so let me try to run it. Okay, now it is going to try to start the image, and let's see whether, wait, if it works, usually it will turn to the green icons in, let's say, 7 seconds. But now it's keep it running. Usually it means all GPUs are used by other users. I cannot allocate a GPU. Therefore, okay, let's stop it. Okay, and try the third image. I just created a few minutes ago, and the specs are totally same. The only difference is the GPU. I don't allocate any GPUs for this image. And let me run it. Okay, it works. So you see, it become the green icon, and then I click the connect. So I will launch the remote desktop. Okay, so that's this part. Okay, if the resources are available, that you can connect it. Okay, however, if you see this error message, no healthy upstream, it looks like this, a very small line. It means the image you just run it is still loading its progress. And the remote desktop is just a part of the program running in the image. So you need to wait for additional, say, 10 seconds, so that, or 5 seconds, up to the cases. And if refresh your browser, then usually the error message will disappear, and you can successfully get your remote desktop. Okay, so this is the remote desktop VNC. It is I should say, widely used. No VNC is widely used. Maybe I'm not sure. Okay. However, our flow system equipped this VNC system, and sorry, there is no English interfaces. So the words here just means connection, and just click it, and you will see this is the user interfaces of your remote desktop. And you are at the root. You can install anything by your own. Okay. Okay. So the image will just like this. Okay. Let's see whether it is shut down or no. It is still running. And let's see. Okay. That's not. So this session has been closed, but this is still running. What I want to remind you is, if the system detects there's a long idle for whatever reason, it means your GPU or CPU is not running for a few while. I don't know how long it will be. The system will shut down your session and recycle those resources for other users. So if you want to keep your session alive, then run something. Just run something. Or just keep using it. Then your session will, you will still own your session for many hours or many days. Okay. Maybe that's the reason why I cannot allocate a GPU just in the demo, because somebody else are using it then right now. Okay, so let's explain it. The Kubeflow is a virtual system. It means it's just like a Docker. Okay, so you have many images. You can load those images into your system, and it works as a virtual machine. So there are two parts. The first part is the image. It contains the operating OS and some pre-installed program. So what is the pre-installed program? From this document, we can see the list here. Okay, so the pre-installed programs include MATLAB, NumPy. All of them are Python libraries, and RStudio, VS Code. Also, they are programs. Okay, and they are the pre-installed programs. Once you shut down or close the session and reload the image, they will totally restore to the default status. If you install any programs or save your data in the images, then you will lose them. So if you want to reuse some programs or save your data, please save in the Valen folder or the Valen disk. So where is the Valen? The Valen is mounted in the folder. Here, this is the home Chih-Yuan. Okay, so the Chih-Yuan, I think this is the username of when the folder was created. However, so if let's see where it is here. So if you open your file manager, you will see the Chih-Yuan folder here. So that is the default path to your Valin. Okay. So if I change the setting of this page here, when I created the image, if I change the mount path from Chih-Yuan to my name, for example, CYYNG, then when I run the image, I will see this result. I will have a new folder. This is the mount path of my Valin, but I will still see the Chih-Yuan in the place because the Chih-Yuan is included in the image. I cannot change it anymore, but I have my own Valin and it mounted to another folder. So that is the point. I mean, you will have a slightly confusing status, but however, it still works. You just see two different spaces. One is your own Valin, and another is the one included in the image. Okay. The another problem is because the image was created maybe 3 years ago, so the default Firefox is slightly old. How old it is? The version is 86, so it was 3.5 years ago. Okay, and the version of Firefox is incompatible with Easy Diffusion. So, okay, so if I want to use Easy Diffusion and I use the default Firefox, I will see the warning messages. Stable diffusion is starting, but okay, so it will confuse you if you don't know it, and it is easy to solve. The first is just because Firefox will automatically update itself. Just turn off the Firefox and turn it on again. Your system will install a new version of the latest version of Firefox, and then you will no longer see the warning message, stable diffusion is running. You will see the correct message, stable diffusion is ready. But however, this is the problem. Every time you shut down your session and reload it again, the pre-installed Firefox again appear in your image. So another way to solve the problem is install a new Firefox in your Valin and use the new one in your Valin so that you won't see the warning every time. Alright, so if you can successfully load an image with a GPU, then you can use Easy Diffusion. It is a package of stable diffusion to generate image like this one, and it only takes 6 seconds because V100 is a GPU good enough, so 600 is enough for it to generate an image. Okay, there's another trick I want to share with you. It is we can create a multiple image just like this one. Oh, sorry. The first image and the third image are totally the same. The only difference is the one has a GPU and another don't need a GPU. So I created the two images and they share the same value. It means when I created the new images, I don't use the default value. And I select an existing value like this one. This is a 512 gigabyte value. Okay, it is used by image 1 and the image 2 together. So there is a benefit. If I don't need GPU for some cases, and I still can work without the GPU, so all of my data will save in the Valent, and I still can work. Okay, so that's the only benefit I know. All right, so I want to give you some feedback for your homework 1 presentation. First, I want to thank all students who share your findings and knowledge, in particular for the papers, because you see for ECCV there are more than 2,000 new papers, and for CPR also there are more than 250 new papers. There are so many papers, and it is impossible for me to read all of those papers. So I really appreciate you who share your knowledge by reading those papers. Okay, and for this is presented by Anqua Wing, right? Okay, and he used images taken by a drone to predict the availability of the parking slots. My feedback is, I just realized there are drones available in our department. We can borrow it for free. And there are at least 2 types of drones. First is a small, very small drone, okay? And the weight of the drone is less than 250 grams. This is important because for such a small drone, we don't need a license, and we don't need to register the drone to the government. You can use it for any cases. Okay. And another type of the drone available in our department is the medium-sized drone. Okay. Then its weight is greater than 250 grams, the threshold. So if you want to fly the drone, you need to have a license. Okay, and you need to register the drone to the government. However, what I want to say is the devices are available. If you want, you can borrow it through me. Okay, then you can do research for this purpose. Okay, so, but however, everybody have his own or her own research interest. I just want to mention we have the resources. If you want, you can do it. Okay. And the second feedback is, okay, so this is Marcus' presentation. Okay, it looks very good. And I have a following question is, what will happen if you apply this algorithm to videos rather than image? So Marcus,
I tried this. This was my first idea to apply it to videos, but it took too much time to process. So I changed to just photo, but it works for video too.
Okay. Good, very good. So how long does it take to process one frame?
I cannot remember.
Okay, so do you use GPU or just CPU?
No, just laptop.
Okay, interesting. Okay, fine. So this presentation reminds me of a thing. It means 13 months ago, I received an email from my PhD advisor. He asked all lab alumni to participate in an online survey. Okay, let's take a look. What is the online survey? Okay, just click here. Okay, so this is the Google Form online survey, and if I click next, and then you will see this is 2 input images, and they are two generated stylized video. Okay, so what I need to do is click which one is better, and then next. another input stylized form, and this is generated results. Okay, so I repeated it for more than 20 videos. So that's all. I just okay, and let's go quickly to some other. This one. Okay. Okay. I want to see some. Okay. Okay. This is another one. Okay. So this is the case. This is the case, and okay. Okay. Let's stop here. So, what are the surveys? Okay. Okay. Usually, I should say, when I receive the email, I know they are doing certain type of research. And the research is, okay, the development of the new algorithm is almost complete. And they need some user study, the data of user study. Okay, so, yeah, I should say 3 months later, okay, in last December, they released an archive paper to work for the human video stylization. So, okay, so what is the paper? So you can see this is the example image. What they want to do is, given the input image, they separate the human subjects and the background. So use nerve. So they can render the sorry. I forgot to turn on the laser pen. They can render the background and render the human subjects. And then they can give a style image to create a what? To create a different viewpoint and create an animated human subjects with the styled image. Okay? So this is why they call it 4D human video subject, because the 4D means 3D. Once you can change the viewpoint, you can create another videos looks like from another 3D render the image. Okay, and you can, because it's a video, so this is another axis, the time axis is a 4D. And it's interesting why they want to do it. When I read the paper, I found the fourth author is I don't know, it's from Snap Inc. So what is Snap? Do you know Snap? Okay, most of you know, and it is okay. So its main product is its app. The app is I should say it's a media map or an instant message map. So, and it is very popular among teenagers. So why do they need to develop this research project? I wonder, maybe Snap wants some new features for their app. So, okay, because when most Snap use the videos taken by most Snap users are human. Okay, so if they can create such a feature, it will create some interesting effect for their users. Okay, so let's see what is the rendered new viewpoint. Oh, this is the input image, and the three are novel views. So what can you spot the difference? For example, the head of the human is very close to the window of the left window, but in the newly rendered viewpoint, it is at the center of the background. So you can see the view angle are slightly changed. Okay. And here again, you can see for example, the head is around the rectangle, but here it moved to the right part of the window, okay, and even more slightly further. So this is the the novel view. And because the foreground, the human subject, and the background can be separated. So for this image, actually this set of image, the actions are rendered, not the input, not from the input image. Okay, so, all right. And okay, so that's the reason why they need to collect the human subjects scores. Because the research is so new, they cannot find a metric to measure the quality of the generated videos or image. They only can ask other human users to evaluate which one is better. So they conducted the human subject study on two different spaces. The first is the original video spaces. Okay, from this chart, you can find their performance is only slightly better than some existing method. For this case, their performance is even slightly worse than an existing method. However, if they take the novel view and animated humans into consideration, then they show, okay, their performance in terms of the human subjective scores is better than existing methods. That is the support to their paper. They need to persuade the reviewers, okay, our method is better than existing methods, so that they have the value to be published. But however, currently, they only have the archive paper. I don't know why they haven't published the paper in computer vision conferences or somewhere else. Okay, maybe the reviewers challenge them for something. And I checked they haven't released their code. Okay, they have a GitHub page, but it's empty. So okay. For another one, this is the Yi-Chen's work. Okay, this is interesting. This paper is very interesting. But I have a few questions. First is, do they release their code? Okay, can you find any open sources implementation for this algorithm? No. Okay, that's fine. All right, and this paper was published in AAAI 917. And it's 7 years ago. Then there usually are some following papers or projects. Do you know any following research based on their paper? Any improvement, any novel component added? That's fine. I just try to suggest you, this is just a habit. If you are interested in certain topic and you found, okay, a paper, but the paper was not the very, very new paper, then usually there are some following papers. Okay, never mind. Okay. Otherwise, do you know who cited this paper? Okay, never mind. But this is just a habit for doing research. Okay, so if you have target, then find what is the latest one? What is the difference? Just keep it in mind. That's right. Okay. And the latest questions. I assume the paper want to play video games by a program rather than by a human being, right? And what is the latest progress for this purpose? I mean, okay. You found a paper 7 years ago, published 7 years ago, so, right? Because this paper was published in AAAI 17. Okay, then 7 years passed away. There must be some new papers or changes during the 7. Yeah. Anything new? Okay. So I just have a question. So if you can answer my question, it would be great. If you cannot do it right now, that's fine. Just build the habit, and because this is the beginning of doing research. Okay, I mean now you are a graduate student, right? No. Okay. Oh no, maybe okay. What I mean is, you are a graduate student now, and you are trying to learn how to do research. Okay. Oh. Okay. So, and you have a starting point because you are interested in this topic. Okay. Yes. All right. But the paper is slightly old because it was published 7 years ago, and during the 7 years, there must be some new papers, new ideas, or new methods. Okay, then what are they? Where are they? Just I suggest you, if it is possible, try to figure them out. Yes. Okay, then that will be your first step to do your own research. You're welcome. Okay, so the slide was used last week, I think so. Okay, so what we talk about was this is the contractive learning. Okay, we saw two different machine learning problems. One is classification, and the second is regression, and this is the third, contractive learning. So for this, so this is the sentence, or I should say, mathematical expressions given in our textbook, and this paper is an example how to use contractive learning to learn something. And what is the contract? It's a contrast between a piece of sentence, okay, and the image. So this is very interesting. One is text and another is image. Okay, so they learn from what? From 4 million pairs of image and sentence. Okay, and once they learn, they just what they learn? They learn the transform matrix. Means given an encoder, they didn't create a new encoder, and they didn't create a new image, text encoder or image encoder. What they learn is the transformation matrix, the W here. It means given an extracted image feature and given an extracted text feature, they try to transform the two features into the same space using the embedding transformation matrix Wi and Wt. Once they learn it, so that they can compare the features in the same space. Okay, so here they show the power of the contractive learning. So let's see this figure. There are 27 data sets. Some of them you may know. For example, CIFAR10 and CIFAR 100. Okay, and ImageNet. Okay, so for the 3 data set and NIST, for the 4 data set you are quite familiar with. And what is CIFAR10? It means 10 classes of images, and each images there are 5,000 training image, and the classes include dog, cat, airplane, ship, etc. And and every image is quite small. The resolution is only 32 by 32. And CIFAR 100 is the extension of CIFAR 10. There are 100 classes, right? And ImageNet, there are 1,000 classes, and the total data set, there are, I forgot the number, more than 100 million images. Okay, so what I want to say is, okay, now they use the 400 million image to track the transformation matrix. Then, okay, the next thing is just use the learned transformation matrix to predict the class of the given image by what? By this. Suppose for Chih-Yuan, there are 10 different classes. They create a sentence like a photo of something. Okay. The something is the name of the classes, and they can create a text feature through a given text encoder and use their learned transformation matrix to transform the text feature to the embedding space. Okay, then given the image just from the CIFAR-10 dataset, use a given image encoder. Okay, so the image, there are many choices for the image encoder. It can be ResNet, it can be EfficientNet, or it can be visual transformer. However, for a specific type of image encoder, they will learn a transformation matrix. Then they can use the learned transformation to create the embedding feature. Just use the cosine similarity to compute the similarity between the image feature and the text feature and find the largest one. Okay. So they can use this method to decide the image belongs to which class. And this is their performance. It means just use the 400 million training data to pre-train the transformation matrix, and then they no longer need any training data from the 27 datasets. They can generate the result as good as images, as good as the ResNet 15 here. So you can see the ResNet 15 pre-trained in ImageNet and then fine-tuned on the 27 datasets. So what does this mean? It means if you have a lot of training images and a lot of captions, then you effectively learn a method which you can create a very, very useful embedding feature. Okay, so let's see here. There are several choices for the image encoder. It can be ResNet, it can be Vision Transformer, and it can be EfficientNet. So they want to know which one will generate the best result. So again, they try. So from this caption, you can find that they tried Vision Transformer, ResNet, and EfficientNet. Okay, so they found their contractive learning is very, very effective. See this line. Under the same computational resources, the G float means gigabyte of a floating operation. Then they can generate the best average accuracy. So the average means they test their method for the 27 datasets. And however, so which one is the best? So they found the Vision Transformer generates the best performance, and the second one will be the ResNet. And compared with some existing method, for example, EfficientNet, their method performs very well. So the paper published in 2021 was the state of the art at that year. Okay, and they also found a very interesting things. The pre-trained model is very robust to different type of images. So let's see here. So this is the images from ImageNet, and if you you find the images banana from another dataset, this is ImageNet V2. They are slightly different from the ones from ImageNet. If you take a look of the ImageNet R, then the banana, what's the difference from the ImageNet and the ImageNet R? The ImageNet are the real world image, but the ImageNet R, first you can see this is the banana toy, and this is a banana, but its background become totally white. Okay, and this is the drawing banana. So if you found banana from the ImageNet sketch, so all of the images are sketching. And if you find the banana from the ImageNet A means art. So all of them are banana, but they are artistic banana. The message, okay, the concept for human beings are the same, they are banana. But for images, the distribution are quite different. So this is called distribution shift. And they found, okay, if they use their clip method and without any fine-tuning, their method can generate relatively better performance than ImageNet trained on ResNet 101 trained on ImageNet and applied on other datasets. So there are two reasons. First, in their dataset, the 400 million training image and text pair, there are many images similar to the ones in the other dataset. Not only the real-world photo, but also the scratch, the art, and the object. And second, because all of the images in that set contains the keyword banana. Therefore, their models learn the concept of banana, not only restrict to the images of ImageNet, but also a variety concept of banana. So this is the reason why this paper was very important when it was published. It shows two important things. First, if you have a very, very huge large set and you have a way to exploit the information in a huge data set, it works. And second, this is the first paper. It shows image and the text, but you can learn something using contract learning to get the information between the two different domains. Okay, right? So we see three different types of tasks: classification, regression, and contract learning. So, okay, now we have a network and we have some tests. And for the tasks, we developed the loss function or loss value. The next thing is, how do we optimize our weight in the network? And currently, most people, and the most important method is back propagation. So what is the concept of back propagation? It means, okay, this is the forward process. Given the input, we have a layer, another layer, and there are several layers. And finally, we will generate the output. The back propagation is when we have an error from the output, we want to calculate the weight among these neutrons and then propagate those errors from the lattice layer to its previous layer and propagate the errors from the previous layer to the first layer. Okay, so among the projection progress, we can calculate the gradient respect to the error and its weight. So how to do it? So for different tasks, for the classification, let's see, how do we define the loss? Okay. Usually we will use a multi-class cross entropy loss, and its mathematical expression is this is the error. And because we have many training instances, so the error is summed up through all of the training instances. And for each training instances, the loss is its probability for that correct class and take the negative log value. Why it is negative log value? Because all probability value must be between 0 and 1. And when you see, let's see a log value. Okay. Right. Okay. So this is the curve of log, and between 0 and 1, okay, the value of log are all negative. And if you take the log negative, it will look like this between 0 and 1. Okay, the log negative curve will look like this. So it means if your probability is close to 1, then the value will become smaller. If the probability is close to 0, then the negative log will become greater. So it can use to measure loss. What is loss? Loss means we want to reduce it as much as possible. So for correct class, the probability should close to 1. So this loss will become smaller. So this is the reason why this is the log value of the probability. Okay. And because the probability is, if we have several classes, the probability, how is it calculated? It is calculated from a softmax function. So what is softmax function? At the end of our network, we will generate several scores. So that is A score, B score, C score. And the softmax, it is just the exponential of those scores and send them up as a denominator. And the denominator is the exponential of a specific scores. Therefore, okay, from the definition of the softmax layer, the error of an instance is the log of the probability. It becomes the log Zn minus the Sntn. And the Zn is what? It's just this one, the denominator term. Therefore, okay, we can calculate the derivative of En respected to Snk, okay, and expressed in this term. So the Pnk is the probability, and the T tilde Nt, what it is? It is just an indicator whether it is 1 or 0. If the Tn is the correct class, then its value is 1, and otherwise its value is 1. So what does it mean? Say this means for CIFAR 10, we have 10 classes, right? And for ImageNet, we have 1,000 classes, right? And because it is a training instance, so we know the correct, the label of the class, correct class. And it is the value of K. So if the K is the correct class label, then we should increase the probability as much as possible. It means we should increase the score SNK as much as possible, so that the loss will decrease. And among the 10 classes or 1,000 classes, 9 or 999 classes are the wrong class. So their TNK is 0. So for those classes, we should reduce their probability. It means we should reduce their scores. Okay, and for regression task, how do we define the probability, the loss function of a regression test? We usually use the squared error term. So what's the definition of squared term? It means y is the value generated by our network, and the Tn is the target value. We just calculate their difference and the square term and sum them up. And the coefficient 1/2 is added for convenience. Therefore, we can calculate its derivative of the error respect to the y value. It becomes y minus TNK, because this is square term. We derive it, the square term, it will be limited by the 1 and the half coefficient. Then we can compute the weight from activation xk. So it becomes xi is the, because the definition of an xi. Si, what is I? Because it's a neuron. So Si is the summation of the activation with the weight vector. And the component or element of the weight vector is Wij. So this is the definition of the summation term, Si. And how do we generate the Y? It is the Si and through an activation function H, and then we generate the value of Y. Therefore, okay, for example, from the figure given in our test on our textbook, so suppose this is S1. How do we generate the S1? It is this x11, x12, x14, and x1, 13, x14 times the weight W11, W12, W12, and 13, and W14, and it becomes S1. And there is an activation function. Then we will generate the output of the Y. Okay, so this is for the S1 case. If we have another S, then we will have the same format. Okay, so this is S2, and S2 has its own activations and its own weights. Okay, so that is the backpropagation. It means we can calculate this. This is the error term for just one instance. And this is the summation for its lattice neutral. We can calculate the E. This means the error term. So how do we calculate it? It is the derivative y respect to s times the derivative of E respect to y. So what is dy ds? It is the derivative of the h function, h is the activation function, and with the value s. And what is this term? So this term, okay, let's see. Oh, okay, let's see here. Okay, so this term is here. the error, the dE dy, it is the value of y times tnk. So we have this term and we have this term, so we can calculate the term ei. And how do we calculate the dEi dE? So this is what we want, because once we know the gradient, so what is the gradient? The gradient is the error respected to weight. Why do we need to know the weight? Because we need to, should we say, okay, because, okay, here. Now, the value of the error is decided by our weights. So we need to update the weight to minimize the error. So how to update the weight? We need to know the gradient. It means the derivative of error respected to the weight vector, so that we can know which is the direction we should change the weight to minimize the error. So back projection, it means this is the first element we need to know so that we can get the gradient. And B is the bias. It is also a weight. Okay, although the symbol is B rather than W, but the conceptual meaning are the same. They are the weight. We need to know these two values. However, so that can we calculate it? Yes, we can, because by definition, this term is the ds dw and the dE ds. And what is dE ds? It is E. We calculated already. And what is the ds dw? So what is S? This is the definition of that. It is a summation of those weight times the actual x. So by definition, we can get the ds dw is just the x, so that we can calculate the gradient for this term. And the same dE dB is like this. So ds dB, what is 1? Why is this 1? Because this is the definition of S. It is the summation of the weight times x plus a bias term. Therefore, ds dB is 1. Okay. So here, this is 1. So the dE dB is just as large as the error. Okay, and finally, we calculate the dE dx. By definition, this is ds dx and dE times dE ds. And what is this? This is wij. Do we know wij? Yes, we know. Okay, because wij is the weight, the value of the weight. So we can calculate the dE dx. It is the weight times the error term. So you can see, once we get the error term, we can calculate the gradient of the weight. We can also calculate the gradient of the previous neutral. The x is the neutral here. Therefore, okay, we get error from the probability P1, P2, and through its the lattice two neutrals. And then we propagate the errors from the two neutrons to its neutrals on the previous layer. Not only this one, but only this one and this one. Okay. So their values are the dEn, dxij. So layer by layer, from the lattice layer to the previous layer and then the previous layer, so that we can calculate the derivative of the error respected to every weight in the network. So this is the backpropagation. Okay. All right. So once we have the gradient, we can try to optimize our network in It means adjust the value of those weights. Okay. And okay, so this is the error. The error is decided by our weight, and if we use Taylor expansion, then it can be this. This is a x hat, a w hat. This is just a point in the big parameter space. And this is the first order expansion term, and this is the second order expansion term. The b is the gradient. This is what we calculate from the backpropagation. And the second term is the Hessian function. And what is the Hessian function? The Hessian function is the gradients of a gradient. So you will see two gradient symbols before the arrow term. And the definition is the gradient with respect to a w and respect to another w at the w hat point. However, the problem is, okay, if the Hessian function is available, then we can effectively or quickly calculate the local minima, because this is the second order Taylor expansion. It means it's close to the point of w hat. Everything is look like a second order polynomial. So the second order polynomial, it's just like a ball. You have a local minimum, and when the point is far away from the center, then the value becomes greater, and we want to minimize the equation. Okay. However, if h is available, then the minimize the w, you can easily calculate it from the approximate point minus the inverse matrix of the Hessian function times the gradient. Okay, but theoretically, if you know the Hessian function, so you can easily find a local maximum, and so that you can move a point, your current weight, and update to the new local minima, and calculate the second order Taylor expansion again, and go to the local minima. But the problem is, usually we have a lot of weights in a neural network. So how many, say for example, okay, say for example, in CIFAR 10, there are 50,000 training image in total. Okay, and there are 1.2 million images in ImageNet. Okay, so if we want to calculate the Hessian function, it will too large to compute. Because why? Because there is an inverse matrix. It is very difficult to compute the inverse matrix. Therefore, to solve the optimization problem for a neural network, usually we use the gradient descent. It means we don't use the Hessian function. We just try, once we found the gradient, we just try different, lengths of step, and to see which one will generate the minimum error value. Okay. So, because there are too many instances to deal with for a neural network, so the solutions, we just use a batch of training instance and update our weight based on the batch of these training instances, and this is called stochastic gradient descent. So the implementation is quite straightforward. First, we calculate the gradient from the back projection. So we get this one. G is the gradient. Okay, and this is our error term from the batch. Okay, the batch is not the batch can be quite large, can be small or large. If it is say 8, then that is a small batch. 32, okay, medium size. And we see here from the clip, the batch of the clip of a clip training is 3. Okay, the batch size 32K, very large batch. Oh, no matter how. Okay, so from batch, we calculate the gradient, and we just update our weight because what's the meaning of gradient? It's the direction the error will increase most quickly. Therefore, when we update our weight, we will go the inverse direction. So it means the negative gradient. So this is our previous gradient, and the direction is negative g, and we introduce a coefficient alpha. We call it learning rate. Why? Usually we will set a very small learning rate, say 0.001, okay, so that we can avoid, I should say, we want to ensure the new step, the new W will generate a slightly smaller error value. Okay. So we saw this slide before. This is when we talk about a new batch normalization. Okay, so here, let's see. You can see this is X5 and X30 and X5 sigmoid. What does it mean? It just means the learning rate. Okay, so this curve, the black dashed line, it means the inception net. Okay. And when they introduce batch normalization method for the inception net, they found they can enlarge the learning rate. So when you see the curve, the horizontal axis means how many steps or they need to update their weight. And if they enlarge the learning rate, so you will see this curve. I should say, okay, let me say. The black dash is the original inception Google Net. And the red dash is the one adding batch normalization to the inception or the Google Net. Okay, so you can see use much less steps. It can generate the performance of the network can reach the same one as the original one. And then compare the red dashed line and the blue dashed line, this one. Okay. What does it mean? It means if you increase the learning rate, so what's the learning rate? So the alpha is the learning rate. If you have a larger learning rate, you will change your weight every time larger. Okay. So they increase their learning rate to 5 times, and they generated this curve. What does it mean? It means you use much. You only use the 20% of your steps. You can reach the same performance. Is this great? Of course, it is great. You significantly reduce your computational load and your training time. So this is the why batch normalization method is very useful and good. Okay, because they significantly reduce the training cost. Okay, all right, and now there's another technique to help us solve the observation problem is called momentum. Momentum means, let's see here, okay. We have a gradient, and we use the gradient to update our weights. But however, what will happen if the gradient is 0? For some cases, it can be 0. Because how do we calculate the gradient? It is the derivative of the error respect to the weight, right? And how do we generate? But remember, we have the several activation functions. For certain range, their slope is 0 or their gradient is 0. For example, this is ReLU, this region. If your value is in this region, then your gradient will be 0. And shifted ReLU, for this region, the gradient is also 0. And this is the softer plus. So for this region, it is also 0. So if you have a 0 gradient, how would you update your weights? So the concept of momentum is, this is the running average of current and past gradient. So this is the new gradient, okay? And the V is the momentum. And so when you have a new gradient, you calculate the momentum from your previous vector and the new gradient with a parameter rho. Okay, so if your gradient is 0 at this moment, that's fine, because your V will not be 0, and so that the V, okay, is a momentum in this loop will not be 0. You can still use to update your weight. Alright, okay, so now you know the gradient, you know you heard of the momentum, so that you can train your network. And also our textbook show an example. This is the playground from the TensorFlow. Okay, so let's take a look of this. Okay. All right. Okay. So now there are two tasks: classification and regression. And for example, this is a classification problem, and there are 4 different distributions: 1, 2, 3, 4. This is okay. Now you need to select your feature. For example, this one. Let's just try the row one. If you want to classify instances of the blue and orange classes, so what feature would you like to use? I will say I would like to use this feature. Okay. And then just run it. And you will see, okay, it will generate results. Looks quite good. Okay. And you can, here, because we only use feature, so we don't use any neutron or so because there's no neutron, so there's no activation function. We just generated this. Okay, let's just stop and then let's go back to our slides. So there are several options. This is the learning rate. So say the default is 0.03, and there are 3 different activation functions plus linear. Linear means no activation function, just use the feature. And this is the regularization term. What is regularization term? So this is the regularization term. You can choose P as 1 or 2. So this is L1 known or L2 known. And this is the regression rate. It means the alpha value in your error vector. Okay. And so this is the easiest one. We just saw this is the, you can control for classification. There are 4 types of data or distribution. You can adjust the noise. If you adjust the noise, you will see, okay, reload. This is, if you adjust the noise, you will find. So this is the most noisy data. There are a lot of blue points. They become far away from the center. And this is the most clear case. The blue point and orange point are well separated. All right, so the feature. Okay, so what the this is a classification problem, and we will generate the y from our. Sorry, I turn this on. We will generate our y. What is the y? Y is the probability of the two classes, and how do they calculate it? So there is a weight, and there is a nonlinear feature function for x. So what is our x? For our x is just the two x's, x1 and x2. So here you can see the different feature nonlinear function. It can be itself identical, x1 and x2, or s1 square, x2 square, x1 times x2, or the sin x1 and the sin x2. Okay. Then for this example, okay, we just generate, we have the feature. If we choose x1 square and x2 square, so this is the x1 square and x2 square, and I will have two weight. A weight is a line on and I will generate the y. Okay, so why this is so? You see, this is logistic. It will convert the score to the probability. And let's go back to this image to help you. Okay, this is the output of the score, and this is software max, and we will generate the probability of the two classes. And here, the equation is slightly different because why? In our textbook, the target value is 0 or 1. But here, in this demo, the target value is -1 and 1. Therefore, the equation to generate target value changes to 2 times the logistic function minus 1. So therefore, if the score is very, very large, then y becomes 1. If the score is very, very small, or the approach to the negative infinity, then the y becomes -1 because the output of a logistic function is 0. The minimum is 0. Okay, you can also manually set the weight. Okay, let's take a look here. Just click it, and you can change the value, and you will see it will create different figures on the right. The orange means negative, and the blue means positive. Okay, so you will see this is the output figure. Okay, and then you will also see the historical log, because what? If you run it, it means you use backprojection to update its weight. So if we reload, okay, so the current weight is 0.27 and another weight is 0.1. If I click the item here, step, it means I update it. So this is become -0.62 and update. When I keep updating it, okay, the generated value, it will become the 1 through this equation, and the target value y will be close to the training instances. So let's see an example. Okay. If I set the noise as 0 and I train the network, get the two parameters W1 and W2 using this equation. So the weight, we say the error is controlled by the weight. So what we want to update is is the weight. So from this weight and this weight, we get this y value. When the coordinate is close to the orange, it means the x1, x2, both of them are very small. Then the y value will approach 1. And when the x1, x2 is at the outer regions, it means they have large value in absolute. Then the y will approach to -1. So it matches the distribution of the two classes. And there's another pattern called the chessboard distribution. It looks like this way. Okay. And when you run it, you will see the weight keep increasing. Why? Okay. The reason is, let's see the cross entropy loss. Okay, it is written in this way. It's slightly different from our textbook because, again, the target value in this demo is -1 and 1, greater than 0 and 1 used in our textbook. Okay, so let's see the error term. If we have only single parameter, the error term won't be 0, even all instances are correctly classified. Therefore, because of the big projection, it will keep trying to increase the weight W1. If the W1 is greater, then the error term will be smaller. That's the reason why it keeps going up, and up. Alright, okay, so you can play it by your own. It's free. So let's take a break for 10 minutes. Alright, so the third distribution or third data type of the classification task is two clusters. So it's easy to solve. If I just use the x1 and x2 feature, it's straightforward because in this case, you will see this is x1 times the first weight, and x2 times the second weight. Okay, then very straightforward. When either the both weight is a positive weight, so 1, 1, etc., then you can easily find a decision boundary to separate the two clusters because they are linearly separable. And the fourth data, it is the spiral distribution. This is the most challenging because can you see? Okay, let me see. Can I enlarge here? Yeah. This is a spiral pattern. This is the most difficult one. And I cannot use any feature, just features, to separate the two clusters of instance. So here, you see, I added the layer. This is the multi-layer the structure of the multi-layer structure. So this is I just used the first layer. If you want, you can use more layers. So let's see, this is spiral. Okay. And currently, if I use the two feature and I try to run it, no, the error rate, the error is very high, 0.5. Okay. If you want to see the test data, click here. You will see the data. And if you add some noisy, okay. So how to do it? Use neutrons or the hidden layers. So if I add one more neuron and turn on all features, and let's try go. Okay, the result is still poor. Let me try more neutrons and go slightly better, but not very good. If I try different activation functions, say relu, and go, okay, and well, not very good. So you can try more layers. One, because do you remember we introduced a theory called it means neural network can approximate any type of function. So here, if we want to find a function to separate the two classes, the set, if we have sufficient neutrons, then theoretically, it can process any function. So it looks like much better than the previous one. Okay? And here, you see, all of them are weight. So in this network, how many weights are there? It means how many curves or are in this on the screen. Okay, so this looks like much better than previous, and the loss is slower. Okay, so you try it. If you want, try it by yourself. Okay, so there are a lot of parameters you can set. How many neutrons, how many layers, what type of activation functions, and what kind of features you want to use. Okay. So for regression, okay, so this is, and there are only two types of regression data. One is looks like the diagonal gradient. Okay, so for this part this is negative, and for this part this is positive. And for the regression test, you have to use at least one neutron, because for the classification function we have a logistic function to convert the output to the probability or the target value. But here for regression, we don't have it. So we need a neutron to convert the weight from the feature to the target value. Okay. So there are ReLU, tangent edge, and logistic. And the latest one is linear. If I use linear, it means the input will be the output. And if I use linear for this case, then there will be a new weight, W3. It will be the W1 plus W2. Sorry, there is no W0 typo. Okay. And let's see here. Okay. If I change this to the regression function, and then the first one, and I reduce those, just a single hidden layer and just one neutron, and the activation function is linear. Okay, and then I just use the 2. It should be sufficient, and run it. Okay, so there you can see this is the first weight, and this is second weight, and this is third weight. The third weight is used in here. This is the third weight. Sorry, this is a typo. This is no W0. Okay. And however, sometimes you will find, okay, your network doesn't converge. It means those weights doesn't converge to the expected value. Why? Maybe your architecture has some problem. For example, for this regression, if you see the black icon, it means the weight value become none, not a number. And why it happened? Because, say, if I use linear activation function and there are two neutral, what will happen? The output of the linear linear weighted sum through a linear activation, it is still linear. It is still linear. Okay, so when there is an error and it back to the two neutrons, it may go to infinity or go to a negative infinity. So it become not a number. But it not always happen. Why? Because we use a batch of instances to update our weight. Every time when you run it, the batch you get from your train data are different. So sometimes it happens, sometimes it doesn't. Let's take a look. If I add two neutral and just run it, okay, it works now. And if I reload and run it, it is still working now. So, okay, it doesn't happen here. Okay, so if I turn all of the features on and run it, No. Okay, sorry, I cannot repeat the problem here, but if you try, you may find it. Okay. And the latest data type is the 6 clusters. Look like 1, 2, 3, 4, 5. There are 6, and they overlapped. So it is the challenging distribution. Again, you need to add some neutrons to try to solve it. Okay. Now let's go back to let's talk demo. Interesting demo, and you can try it by yourself. And from that, now you have a network architecture, and you have many weights, and what you want to do is update those weights through back projection, and then try to minimize the final error number. Okay, so I should say that is the concept of neural network, and the neural network has been used to solve many computer vision problems 20 years ago. So this is the Net 5. It was developed 26 years ago by Yang LeCun. Yes, so Yang LeCun is the winner of the Turing Award 2018. Okay, so let's take a look. So this is the input image, and then there is a convolution. Okay, this is just a weight of there's several weights to calculate the region and generate the convolution result, and it will become several. So this is a set of feature maps, and then through a max pooling, it will reduce the feature maps resolution, and then do a convolution again, and do a maxima pooling again, and then flatten those three-dimensional activations into a long vector. And so that this one and this one is the multi-layer perceptron, and finally it will generate the output probability. But here, Yang LeCun didn't use softmax. He used another approach called Gaussian RBF, radial basis kernel. Okay, but the structure, the architecture of the network is the same. So there are how many layers? There are 5 layers. This is the first layer. This is the linear weight summation, and to generate this one. This is not there because this is a maxima pooling. It just simply reduces some pixels. So this is the second layer, and the maxima pooling is not there. And this is third, fourth, and fifth. There are only 5 layers. Okay, here we saw these figures several times. So just like the discussion between Kench and Professor Ma, okay, that is not a deep learning, because if you use cascade ADA boost, then the feature is mainly crafted. But however, for this AlexNet, where is the one to extract the feature? How is the feature extracted? The feature is extracted by the convolutional kernels. We don't design those convolutional kernels. We just ask the network learn the kernels by itself. How? Try to reduce the final loss value. Okay. So here, the learned feature learned from the convolution kernel, and this convolution kernel, okay, is this block learned feature. So let's recall what is a convolution. So we saw this slide in our second course. So convolution means given an fx, an image, and a kernel then it will multiply this pixel to this pixel to this pixel to this pixel to this pixel, because this is negative. So convolution is very similar to coefficient filter, but the order of the pixels are different. So here we see this is a feature map, and this is another feature map. How do we generate? What is the relationship between the two feature maps? It means, so suppose this is a feature map. The resolution is h times w, and there are several channels. See, let's see here. The input, it is a grayscale image. The number of channels is just one. It's height, width, and grayscale. And if it is a color image, if this is a color image, there are three channels: green, blue, and red. Okay. So when we have the convolutional networks among, so here we generated 6 channels. Why do we generate 6 channels? Because we use 6 convolution kernels. Every convolution kernel will generate a new layer. And here, if we have 6 layers, and we have a convolution kernel, its size is 3 times 3. So what will be the depth? The depth will be 6. How many channels are in its previous layer? So how many channels will be the convolutional kernel? So we have 4 convolution kernels, 1, 2, 3, 4. Each of them will convolute the previous layer and generate a new channel. So, and we concatenate the 4 channels into a new layers. So that will be a new feature layers. And let's go back to the simple AlexNet. So here, Yann LeCun used 6 convolution kernels. So the first layer have 6 channels, and through the maximum pooling, the number of channels are the same, 6. So you can see the number 6 here, and the resolution is 28 by 28. And then it applied 16 convolution kernels to the second layer. So you generate the second layer. There are 16 channels, okay? And each of the channel, the resolution is 10 by 10. Okay. So in this case, okay. All right. So that is the concept of convolution, and we use batch, right? Because we want to calculate the gradient from the batch. So it means we not only have a single input image or single input of convolution, feature maps. We have multiple feature maps. It is the M here. It means the number of batches in the number of instances in a batch. So here, the channel in means, okay, for a single channel. For a single layer, we have how many channels? And the layer width and the layer height, and times the batch size. Okay. So this is, if we do the convolution for a whole batch, it will look like. So here, we use 6 kernels, and the generated new layer will be 6 channels, and so for this block, it is generated by the first instance in the batch, and for this block, it is generated by the latest instance in the batch. Okay, so this is the how do we do for the to calculate the new convolution layers from a batch. And what is pooling? So as we show in this image, pooling is a method to reduce the dimension. If we so for example, suppose this is a layer, our input layer, and pooling means we calculate if the pooling size is 2 by 2. It means we take a look of this window of 2 by 2 pixels, and there are two different type of pooling widely used. One is max pooling. Max pooling means for the 4 values, we just take the largest one and ignore the remaining, I should say, activations or feature, the value on the feature maps. That's fine. Okay. And for then we take the look of this window. So what is the maximum value among the 4 values? It is the 522. So we take the value and assign it to the new image or to new feature layers. So the same. So as a result, you can see the input resolution is 6 by 6. And through a maximum pooling 2 by 2, then we will generate a new feature maps. The resolution is only 3 by 3. Okay. Currently, maximum pooling is more widely used than average pooling. But in the AlexNet, Yang LaQuan use average pooling rather than maximum pooling. And what is the benefit of using pooling? Because let's see this example. Pooling can provide a shift invariance. So what is shift invariance? It means, say this is digital 3, right? And this is another digital 3. They are totally identical. So for our network, what we want is, no matter your input image is this 3 or this 3, you won't generate the same predicted result. Okay, so how do we overcome the problem? Because their locations are slightly shifted. So if you have the maximum pooling, it means you do some convolution, and you will find the most significant response, for example, this one. And when you do maximum pooling, you will ignore the remaining less important signals. Then, if you do the maximum pooling several times, then you will ignore the shift on the original image. So this is called shift invariance. Okay, then let's see what is unpooling. So you see pooling. Pooling means, given, for example, this patch, the file will be preserved. 9, 6, 8, and 5 will be preserved, and all other values will be ignored. Unpooling means you remember the location of the source of those pixels. So this is the black regions in this figure. And then when you have a set of new value, use the information and restore the values to its positions. So this is unpooling. And there is another term called upsampling. Upsampling is similar. If you get these values from its previous layer, use maximum pooling. And then upsampling means restore the value to every pixels of the restored image. Okay. So why do we mention it? Because there is a technical called, there is a method called transpose convolution, and it is also called deconvolution. It means, see here, we use convolution we use a convolution kernel to calculate the value of the 9 pixel to a single pixel. Can we do it reversely? From a single pixel to restore the 9 pixels in its previous layer? Yes, we can. So that is the transpose convolution. Why is this called transpose? Because let's take example. The blue region is the input feature map. Say it's only 4x4. And if we have a kernel resolution convolution kernel, the size is 3x3. So what we will generate? We will generate an output feature map. It is 2x2. So for this region, we convolve the 9 pixels to this one, and this 9 pixels to this one, this 9 to this one. If we vectorize or factor this input image to a long vector, so for this one, the vector will have 16 elements, and for this one, the element will have 4 elements, and then we can write it as this is the input vector of the input image, and y is the output image. So the weight of the convolution, it means W00 to W22, can be expressed as a metric. It is C. So it is the convolution can be viewed as a matrix operation. Then, because it's a matrix, so what will be the transpose metric? It will be used to calculate the back projection. So what is the back projection for this term? So this is the error, and this is a certain neutral or certain activation. It means something wrong. I use a wrong symbol. Sorry. This should be E rather than L. Okay. So this is a dE, dy, dx, and the dL, what is dy dx? So this is, if this is y and this is x, dy dx is the elements in the matrix. So I express it as Cij. And how to calculate this one? This vector times Cij. It will be the transpose of this vector times the original vector. Okay, and so this is why it is called transposed convolution. And what does this mean? It means if you if you want to inverse a convolution, it means you can apply another convolution to your input vector. So in this example, the green pixels are our output matrix or output layer. Here, okay, we want to reconstruct we want to reconstruct the 4x4 layers from the 2x2 layers. So what do? We can introduce a new kernel. It is 3x3. Then it will be convolute with the padding boundaries. Then we convolute this region and generate this pixel. Convolute this region and generate the pixel. So we can reconstruct the source layer from the output layer. So what can it be used? So this is the convolution network. This is a method proposed 9 years ago, and for semantic segmentation. So suppose this is an image of a dog, and semantic segmentation means I want to label the pixels belonging to the dog. Okay, so how to do it? In their proposed deconvolution network, so this is a convolution layer, and so you can see convolution, maximum pooling, convolution, maximum pooling. Do it several times, and they will generate a 1 by 1 pixel. And then here they use unpooling and apply several convolution kernel. So what is this? That is the deconvolution operation. And upsample it again. So the resolution from 7 by 7 becomes 16 by 16, 28 and 28, 15, 6 by 6. Every time you apply a uppooling, you will increase the resolution. But there will be a lot of empty or zero values in your newly reconstructed layer. So they need to apply the deconvolution to fill in those values. Okay, let's take a look. Okay, so this is their input image, a bicycle, and then they see through their convolution network, they will generate an image of 16 by 16, look like this. So this is the image of 16 by 16. Unpooling, so they will generate an image 28 by 28, but there are a lot of zero. Okay. Then they learn a kernel to reconstruct the deconvolution images. So from this to this, and unpooling again, they will generate an image like this, 15 by 16, and learn another set of kernels to reconstruct this image. And unpooling again, deconvolution again, unpooling again, and deconvolution. So from this image, they can use the response to predict whether the pixels belong to the bicycle or the background. And okay, let's talk something else. So for segmentation, there are three different types of segmentation. So this, given the image, semantic segmentation, what does it mean? It means if this is the sky, ocean, and the beach, and there are three people, they are the same. Because their semantic meaning are the same, all human beings. And there's another type of segmentation called instance segmentation. It means for this person, and then this person, they should be treated differently. So this is three different layers. And there's a combination of semantic segmentation and instance segmentation. It means panoptic segmentation. It means for different classes and for different instances, they should be treated differently. Right? So let's compare. This is a deconvolution network. Okay, so deconvolution. So this is a fully connected network. It is also to try to solve the semantic segmentation problem. It was published in CFR 15, and when is the month of CFR? It's June. CFR always take place in June. And this paper, deconvolution, it is published at ICCV the same year. So when is the month of ICCV? October. It's always take place in October. Okay. So this one, fully connected network, is a 4 months earlier published. Okay. So let's take a look. Let's say, given an image, there are several convolution layers. And finally, they use the convolution layer to predict whether the pixel belong to the dog, the cat, or the sofa, right? So what's the difference? The only difference is this part. The deconvolution network has the deconvolutional part, and the fully connected network doesn't have the deconvolution part. And they show this figure in their paper to illustrate the difference. So given the image of dog, fully connected layer, it will generate the result like this. And the layer deconvolution layer will generate the result like this. So this is better than this, much more clear. For the details, for example, the head of the dog is clear. And for another case bicycle, and this is the result of the fully connected, and this is the result of the deconvolution network. It is much more clear. For example, this is the left leg of the cyclist. In fully connected, it was treated as the part of the bicycle. But in their result, they separate it from the bicycle. So this is better. And why they can generate the better result? Just because they introduce the deconvolutional network. And why can they introduce the deconvolutional network? Because the transpose convolution was released a few months earlier. So somebody developed the transpose deconvolution, and they used the new technique to their network to solve the problem. Okay, this is the unit. It is also a network developed for the segmentation problem. And this is the figure from our textbook. I want to highlight. So, okay, from this network and this network, what's the difference? What's the major difference? The major difference is there is some skip connection. It means when they generate some feature maps, they just copy and paste to its destination. And this is the second layer. Again, it copy and paste the feature values to the destination and do it several times. And okay, this figure was cropped by the paper. From this to this, I think why I need to do it, because here from those arrows we can clearly see what is the upsample convolution. It was used here. This is the green arrow. This, and this, and this. This is the upsampling convolution. Okay, that's the again. It used the transpose convolution or deconvolution method. And okay, why the unit is important? If you take the important is it requires very few training images to train a network, and the result is also good. So the paper was published in MICAI. MICAI stands for Medical Image Computation and the Computer Assisted Intervention. This paper was not published in either ICCV or CPR. MICAI is the conference focuses on medical images. Okay. And why it is important for medical images? Because medical images are expensive and difficult to generate rather than the real-world photos. So this is the reason unit is when it was invented, it was quickly used by a lot of medical researchers. All right, so we saw AlexNet. We saw LANet. It was released in 1998, and this is AlexNet. So AlexNet is you can see input image convolution, first layer convolution, maxima pooling. This is first layer maxima convolution, reduce the resolution and something slightly different. Okay, there should be a convolution, but I don't know. It is not shown in this figure. Something maybe they combine it together. However, okay. So I want to say the LANet was developed for classified digits. Okay. And the AlexNet was developed for the ImageNet challenge. So the output is 1000 probability value. And the input resolution is 227 square. So it is much larger than the input of LANet. So how large is the input of the LANet? 32 by 32. So this is almost 8 times larger. Okay, so because it's 8 times larger, and there are 3 channels, so it can be used for the real-world photo. Okay, and there are 8 layers, and okay, so this is AlexNet. The structure of AlexNet is almost the same as LANet. Even there are slightly more, 3 more layers, but what does it use? Convolution, maxima pooling, and okay, finally, they use the 3 fully connected layers. So in terms of architecture, almost the same as LANet. Okay, but however, it significantly reduced the error rate from its previous I should say, from the winner of the ImageNet challenge previous year. So in 2011, the error is 25. This is the result of AlexNet 16. Slightly, I should say, significantly reduced. And 1 year later, the zero and the focus network, it is, okay, let me say, what is this network? This network, okay, here, there's a question. So there are 96 channels, right? Why do we need to use 96? Why do you use 200? Why don't you use 200, 300? And there are 256 channels. Why don't you use 600, 500? Can you tune the hyperparameters? Yes, you can tune. You can try different combinations to tune the and why there are 4. So for this vector, why it is for why there are 4k neutrons? Why don't you use more neutrons? Because if you use more neutrons, maybe the result may be better. So that is the result of the zero and the focus. They tune the hyperparameter, and they found if they try to use more channels, then the performance will become better. So the error rate further reduced. Okay, and then the VGGNet. So see, this is the VGGNet, and this is Google Net, and this is ResNet. Okay, and they published in the following 2 years. So what is VGGNet? This is the structure of the VGGNet. There are 4 different settings. So we say VGG16 is this one. It uses 16 layers. And this is VGG19. It uses 19 layers. And VGG, compared with the previous one, AlexNet only uses 8 layers. And the VGGNet uses 19 layers. So it becomes a deeper network. And the most interesting thing is VGGNet is very, very regular. So see what type of convolution kernels they use. Convolution conv3. Except the convolution 1 you can find. All of them are convolution 3. So this is another issue. Why don't they use convolution 7 and convolution 5? Why don't they only focus on convolution 3? Okay. Nevertheless, they propose this network, and its performance is very, very good. State of the art in that year. Okay. So you can see they also generate 1,000 probability values. This is network designed for EVGNet challenge. Okay, so this is the performance. You can see, so A, B, C, D, E. This is the 19, 16, and this is 13. So if you increase the number of layers, and let the network become deeper, the performance become better. So from 10 is, and this is top 1. So top 1 and top 5 means if you can, if you will generate 1,000 probability values, right? If you only pick the highest one as your result, then you can compare with the test data whether your prediction is correct. But the top 5 means you can pick up the top 5 classes, and if the ground truth classes match one of the 5 classes you pick, it counts correct. So that's why top 5 error rate will be much less than the top 1, because top 1 is much more difficult. Okay, so this is the GoogleNet. It was also published in the same year as VGNet. So let's take the performance. GoogleNet and VGNet, they are slightly close to each other, but the GoogleNet is more deeper. There are 22 layers. And this is the GoogleNet, the full figure of that. So there are 22 layers. Now let's take a closer look. Okay. So here, if you see a convolution here, this means this is a layer, another 2, 3, and 4, 5. Okay, so totally 22. And see this for this for this shape, this. Sorry, I didn't turn on the laser bit. Okay. So for this region, and for this region, and for this region, they all look like the same. So it's an inception module. It means given a previous layer, how do they generate the next layer? As you see, AlexNet and LANet use a single convolution. I should say, use a fixed sized convolution kernel, right? But the GoogleNet, they try to introduce another way. It means given the layer, there are many channels. They first use the 1-by-1 convolution kernels to reduce the number of channels, and then apply 5-by-5 convolution and 3-by-3 convolution to generate new layers, and then concatenate those new layers together, become the next layer. And so why do they use 1-by-1 convolution? The 1-by-1 convolution was published in this paper, Network in Network, okay, in iClear 2014. Okay. So let's take a look. So in the Network in Network paper, they proposed 2 concepts. One is the NLP convolution, and another is global average pooling. So let's take only the NLP convolution first. So what does it mean? So this is a typical convolution kernel. Given an input layer, use a convolution kernel, so you can generate the new value of the next layer. And they propose, given after the convolution, then add 2 1-by-1 convolution kernels. So to generate the new kernel values. So from this implementation, you can see this is a typical convolution kernel, 2D, and they introduce the 2 1-by-1. So this 1-by-1 means the kernel size is just 1. And why do they introduce the 2 1-by-1 kernel? Because they can add more nonlinearity, and they won't introduce too many new weight or too many variables. Okay, and they show. Oh, okay, so this is another. So this is the multi-layer perceptron convolution, and this is the global average pooling. We will talk about this in the future because it's useful for image visualization. So, okay, this is the network. Network in network. The name is network. And then they show. Compare with the state of R method, it is this one. Makes out network and the regularization network. So pay attention to the authors of this work. For the paper 8, Yosha Benjo, who is he? He is the, okay, so in 2018, there are 3 winners of Turing Award, Yang LaQuan, Georgia Hinton, and the third is the Yosha Benjo. And who is the author of the paper 15? Yang LaQuan here. So you can see, they all show here. Yang LaQuan, Yosha Benjo, both of them are winner of Turing Award. And their network generate better results than the state-of-the-art methods. Okay. So what is the one-by-one convolution? So this is height and width, and there are many channels. Use a one-by-one convolution, you can reduce the number of channels into a single channel or the number of channels you want. So it is useful and cheap method to increase the nonlinearity of the network. So it is quickly used by Google Net. And here you also can see the one by and the VGG net. See the order. First, MIN was published. Then it is quickly used by VGG and then quickly used by Google Net. So when you have an idea and publish it, it was very, very quickly be used by other researchers. Okay, so that's the talk of the lecture of our course today.